What is the difference between invasive and non-invasive BCI? Imagine controlling a robotic arm just by thinking about it or helping someone communicate without speaking. Brain-computer interfaces are making these ideas real. But not all BCIs work the same way. Some involve surgery, while others don't. That's what we're here to explore today. Invasive brain-computer interfaces involve placing tiny electrodes directly into the brain tissue or on its surface through surgery. These electrodes sit very close to neurons, allowing them to pick up detailed signals from individual brain cells. Because of this close contact, invasive BCIs can detect very precise brain activity, which is perfect for controlling complex devices like robotic limbs or deep brain stimulation for neurological conditions. The process usually takes several hours and involves a surgical procedure that can last from 1 to 4 hours. The electrodes are often made of biocompatible materials like platinum or iridium and are connected to a small device implanted under the skin. The cost of invasive BCIs can be quite high, sometimes reaching tens of thousands of dollars, and the surgery carries risks like infection or brain damage. But the upside is the high-quality signals they provide, which are essential for detailed control and research. Non-invasive brain-computer interfaces don't require surgery at all. Instead, they use sensors placed on the scalp, like electroencephalography caps, to record brain signals from outside the skull. These sensors detect electrical activity generated by neurons firing in the brain. Since the skull and skin act as barriers, the signals are weaker and less detailed than invasive methods. This means non-invasive BCIs can't isolate signals from individual neurons but instead pick up broader patterns of brain activity. They are much safer and easier to set up, often taking just a few minutes to place the sensors. These devices are typically used for simple tasks like controlling a computer cursor, playing brainwave-based games, or neurofeedback training. The cost is usually lower, ranging from a few hundred to a few $1,000s, making them more accessible for everyday use. However, the trade-off is less precision and more interference from muscle movements or electrical noise. There is also a middle option called semi-invasive BCIs. These involve placing electrodes on the surface of the brain beneath the skull but not penetrating deep into brain tissue. They offer better signal quality than non-invasive options but with fewer risks than full invasive implants. These are often used in experimental settings or for specific medical treatments. From a science perspective, invasive BCIs might seem like something out of a sci-fi movie, tiny wires poking into your brain to read your thoughts. It's a bit eerie but also fascinating how precise these devices can be. Non-invasive BCIs look more like high-tech headbands or caps, reading brainwaves from outside your head, which feels more like a gadget straight out of a futuristic story. The challenge with non-invasive devices is how they manage to pick up faint signals through layers of skull and skin, often battling noise from muscle movements or electrical interference. In summary, invasive BCIs involve surgically implanted electrodes that give detailed signals but come with risks. Non-invasive BCIs use sensors on the scalp, are safer and easier to use but provide less detailed data. Semi-invasive BCIs sit in between, offering a balance of safety and signal quality. These differences shape how scientists develop future brain-computer technologies and what kind of applications they can support. Whether for medical breakthroughs or futuristic control systems, understanding these types helps us see where brain-computer interface development is headed.